So when Cora Fisher and Sarah Higgins, the co-curators of The Future We Remember, were imagining this exhibition and thinking about how artists were looking at artifact and object to think about the future, they kind of were thinking about how do we do that now? Like, what do we do with objects when we want to think about the future? And of course, it's time capsule. So they came up with this, what I think is just a brilliant idea, to have the artists contribute what they would bring as a time capsule if they wanted someone in the future to look at where we are right now. So the artists contributed the time capsules, and when you get a chance, those are all displayed here, and I think you'll walk in there. Cora's going to give a walk around, and we'll be sure that you see the time capsule, the other time capsule objects. So then, because we don't usually stop there ever, we decided to have a talk series, of course, around this exhibition. And so Sarah and Cora thought how interesting it would be if we brought in some humanists and scientists to be the interpreters of the objects that were contributed by the artists. So that tonight is the first one. We're thrilled about it because Dr. Kannappan, that Cora will introduce, is an astrophysicist, and I just wanted to be able to say that. I don't get to say that every day, even here. So we have 5 time capsule talks, and Andrew, the anthropologist, is next week. This will really help my brain in April. We have John Mintz, who's the state archaeologist. He'll be speaking and having this conversation with you. The one in May is Dr. Atala from Wake Forest Innovation Quarter, and the last one has been moved. So on your sheet, it says that it's June 3rd, but is actually the week before, May 26th, which is the Thursday before Memorial Day. And that's going to be the poet Sheila Kannappan. I can't really start this talk until we say how thrilled we are that this was sponsored. This idea caught some excitement by people who thought that it was worth supporting. And so the North Carolina Humanities Council was one of our supporters of this program, and the Wake Forest Innovation Quarter also supported this program. And then I guess you guys know that following the talk with the astrophysicist, we're showing 2001: A Space Odyssey. Alex Brown, who's manning the camera, is the curator of our film series, this film series. Can't believe it. Tell me the name of the film series.
Things to Come.
Things to Come. And then after Andrew, the anthropologist, we're showing the original Planet of the Apes. Again, pretty clever. So I think that's all I need to say, unless Cora, you can think of something else that I was supposed to say in this segment. The way this is going to work is Dr. Kannappan is going to speak a little while, then Cora and Sheila are going to talk with you and each other about the time capsule objects, and then we're going to do a little walkabout and a participatory thing. So it should be an interesting hour.
Thank you so much, Debbie.
You're welcome.
Thank you so much for all of you for being here. I'm really excited because the spirit of this evening is about the intersection between art and science, basically. And also, so many of us are mystified about what is contemporary art? Well, contemporary art is something that allows us to, first of all, it's made in our midst, but it's something that allows us to think about what's happening now, but also to even examine a little further, what does contemporaneity mean? What does that mean to be of this time? And how does that relate to the past? And how might that relate to the future? So we're here to kind of use our imagination and also hear from a really extraordinary scientist and scholar. So I'm going to read Dr. Sheila Kannappan's bio because it's very decorated and I haven't memorized it, unfortunately. So Dr. Sheila Kannappan is currently an assistant professor in the Department of Physics and Astronomy at the University of North Carolina, Chapel Hill. Her research interests involve multi-wavelength observational research on galaxy formation and evolution. And her research has led her to international collaborations through involvement with a program called the Resolve Survey and the Laduma Survey. She's also been, I hope I'm saying that right, she's also been involved with the design and implementation of numerous optical and infrared instrumentation. So that's another really exciting thing to think about, the tools that a scientist might use to interpret time, space. Sheila received her undergraduate degree in physics, magna cum laude, from Harvard in 1991, after which she became involved with the Teach for America program. Between 1991 and 1993, Sheila taught at Edwards Junior High in Rocky Mount, North Carolina. And afterwards, she continued her education at Harvard and completed both her master's in history of science and doctorate in physics in 2001. So please, A Space Odyssey, let's have a round of applause for Sheila.
So thank you very much, Cora and Debbie. So first I want to find out how many of y'all are artists? Raise your hand. How many of you are scientists? Raise your hand. How many of you are both? How many of you are neither? Okay, so that's great. So hopefully we will have some fun dialogue, and this is not meant to be me talking at you, so just interrupt, ask questions, have discussion. I have very few slides. I really just want to get us thinking and brainstorming, because the idea was to make some connections we don't usually get to make. Right and left brain stuff. So this is some kind of a beautiful visualization slash, can you hear me in the back? Okay. Some kind of beautiful visualization slash possibly a real simulation. It looks a little bit like the real one they've been circulating, but I think there might be some artistic license taken here, which is showing the recent discovery. How many of you are aware that gravitational waves were recently observed for the first time? Okay, almost everyone. That was really big news. Let me just tell you, that is the physics discovery of the century. So it's a really big deal. So if you didn't know about it, go read about it. And I will make that connection in a moment, but first I'm just going to talk about what astronomy does. So as astronomers, we are not experimenters. We don't get to go out and tweak the universe and see what it does, right? So we are observers. It's an observational science by necessity. And what we get from space, what we observe, includes three things, all of which are here coming from this. This is a galaxy that, in this artist's conception, has a black hole in the center that is beaming stuff at us. It's probably it might be a quasar, or some sort of really energetic nucleus there of the galaxy. So it's sending us three things. Here at the bottom, we have cosmic rays. So cosmic rays are actual particles. So ionized protons, for example, are cosmic rays. Well, sorry, not ionized protons. Ionized hydrogen is protons. So that's an example of a cosmic ray. So these are actual charged particles that have come from very, very far away, and they're impacting our atmosphere. And once they do, the interaction, oh, sorry. I guess I wasn't supposed to touch that.
That's okay.
No, you can't.
Will it go away?
Yeah, it will.
Okay. The actual interaction with the Earth's atmosphere causes particles to create a shower of interaction products, and that's what you see coming out there. So you can tell where the cosmic ray came from in terms of its immediate direction when it hit the atmosphere. You can tell how much energy it had because of how many particles it generates and what they are. You can tell what type of cosmic ray it was. But what you can't really know, and this is the frustration of people who study cosmic rays everywhere, is where it ultimately came from. Because as you see, this thing took a winding path, right? So you can't really say, oh, this cosmic ray came from this direction, so I just look there and I'll see where it came from. That's not going to work. So cosmic rays, although that's something astronomers use, we haven't learned so much from them. Neutrinos is another thing we observe. So this imaginary galaxy is sending us neutrinos along this dashed orange line. Neutrinos are the least interacting normal particle that we know of. And by normal, I'm excluding mysterious dark matter that you may or may not have heard of. But in terms of the normal stuff that you learn about in chemistry and physics and that our world is built out of, neutrinos are the least interacting particle, the least interacting material particle. They have a very, very tiny mass, so little that for a long time people thought they had no mass and were just like light, but it turns out they do have a very tiny mass. But it's not enough for them to really interact very often, so they normally just stream right through us. And so right now, you have bazillions of neutrinos streaming through you, and they're not bothering you. They're not causing cancer, they're not doing anything to harm you in any way. And they stream right through the Earth for the most part. But some of them, a very small fraction, do interact with material in the Earth. And so there are huge experiments designed to detect them, and they'll have like a lake's worth of ultra pure water in order to detect just a handful of neutrino interactions. That's how bad they are at interacting with things. So they do come to us directly, and in that sense they're great. Like we could look back and say, oh, okay, there was a quasar in that direction, or there was a supernova in that direction. But unfortunately we just get so few of them that it's pretty hard to learn a lot from them. So then the third thing, which is what most of our astronomical knowledge is built on, is electromagnetic waves, which is light, right? So this is why we think of astronomy as a visual science. It started out, in fact, as light that we can see with our eyes, so that's in the visible range, but it now spans a huge range of wavelengths that aren't necessarily visible to the eye, going all the way to the radio or microwave wavelengths at the long end. So it's a common misconception that radio has something to do with sound, but it doesn't. So radio waves are light waves that travel with very long wavelengths through space, and then your radio takes those radio waves and converts them into sound waves. But radio waves that in and of themselves are actually a form of light, a form of electromagnetic radiation. Microwaves, infrared is just past our human vision range. So infrared light, as you might know, the military, for example, uses it to see in the night through special goggles. Optical light, that's what we see. Ultraviolet is the more energetic wavelengths at the other edge of what our vision can process. Ultraviolet, you could think of as, well, this is like the white light that, sometimes if you go into a dark room and you're wearing white and they have all the lights off, but they just have, what do they call it, black light on, then you can see more of the ultraviolet. It's just, normally our eyes are very insensitive to ultraviolet, but you can pick it up a little bit. And then X-ray is obviously beyond our vision, but it does interact very much with our bodies. This is where you do start worrying about how many X-rays have I had, and it's going to give me cancer, and so on. And finally, gamma rays, which are even more energetic than X-rays. These are all accessible to modern astronomy, and we use all of them to try to understand the universe. I did want to point out that these two, cosmic rays and neutrinos, those are both actual things impacting us. So you can think of that as like the wind of space coming to us. Whereas, light, obviously that's energy, not a material particle. So light obviously travels at the speed of light. And since it travels at the speed of light, that is a finite speed. And so it takes a finite time to get to us. So in astronomy, when you look at something from far away, when you look at the light coming from something far away, you're seeing the light that was emitted long ago, because it took a finite time to get to you. So one of the cool things about astronomy is that we do look into the past the further we look away in the universe. So this is just kind of an artist's conception of the Hubble Space Telescope. Looking back in time, here's, oh, sorry.
It's okay. I didn't do anything.
Well, it'll go away. So we have the Big Bang. Of course, the Big Bang, this is creating misconceptions. The Big Bang is not an explosion. The better way to think of the Big Bang is that it's not, the universe does not expand from a point. Rather, you could think of it as the two-dimensional analog. Our brains can't really wrap around the 3 dimensions, but the two-dimensional analog would be the surface of a balloon. And as you blow up the balloon, it expands everywhere. The surface expands everywhere. So in 3 dimensions, the best thing I could explain it to you as is like an infinite raisin bread. If you were embedded in an infinite raisin bread, all the raisins are moving apart from each other. And at some point in the past, all the raisins were in one place, but that was all places because all of space-time was a singularity. So that's kind of, I mean, we don't know how to visualize that, so this is kind of inaccurate, showing how the Big Bang is at the beginning. But then over time, as cosmic time moves forward, we get to the birth of galaxies, 400 million years after the Big Bang, 1 billion years after they have completely sent out a lot of ultraviolet radiation and completely ionized. This red is meant to indicate hydrogen gas, so they've completely ionized the hydrogen. Now the universe becomes transparent. So conventional optical astronomy is possible out roughly to this point where the universe becomes transparent. And then many, many billions of years go by. Here's 9.2 billion years ago. That's where the sun, earth, and solar system have formed. So now we can start thinking about life on Earth perhaps evolving at some point after that. Earth didn't exist before that. And here we are at 13.7 billion years. That's the present. And Hubble Space Telescope looking back and seeing all the galaxies, looking back in time. So on February 11th, 2016, the LIGO collaboration announced the first direct detection of gravitational waves. What does this exactly mean? It's not electromagnetic waves, it's not neutrinos, it's not cosmic rays. Something new. These are pictures of the detections of gravitational waves at 2 different sites, one in Washington and one in Louisiana. They are effectively detecting ripples in space-time. So these are undulations in the underlying fabric of our universe that they are detecting. And from these 2 separate detections, overlaying them from 2 completely separated locations, they found the exact same signal. So they know it's real. That's a key thing. So what I'm going to show you, and then this is a matching signal generated from a computer simulation suggesting that the best way to explain this signal is from the merger of 2 black holes. 2 huge, 30 times the mass of the sun, black holes, spiraling around each other and merging together create these huge ripples in space-time that they detected. Now, to help you understand that more, I'm going to play a little video that the New York Times made. trying to get out of my PowerPoint. It's not letting me. There we go.
From the dawn of our species, what we know of the universe has come from what we could see, from light. Visible light for the first stargazers, ultraviolet and infrared light for the Hubble Space Telescope, microwaves and radio waves blasting from the cores of galaxies. But there are other vibrations we can't see. 100 years ago, Albert Einstein proposed his theory of general relativity. He predicted that the acceleration of massive objects would roil the fabric of space and time, sending out gravitational waves. Nobody had detected one until now. 1 billion years ago, in a distant galaxy, a pair of black holes circled each other. They spiraled inward and finally merged. The collision unleashed the energy of 1 billion trillion suns in a fraction of a second. That energy is still spreading outward in the form of gravitational waves, space-time distortions rippling across the universe at the speed of light. As a gravitational wave travels, it compresses space in one direction and stretches space in the other, like sound going sideways. This push and pull weakens with distance. The wave fades to a whisper, so faint that physicists long thought that gravitational waves would never be measured on Earth. But in Louisiana and Washington, two of the most sensitive detectors ever built have been waiting and listening. Astronomy has grown ears. This is LIGO, the Laser Interferometer Gravitational Wave Observatory. Each detector has an L-shaped antenna with arms 2.5 miles long. Inside the ends of each arm, mirrors of ultra-pure glass are isolated from the noise, heat, and vibrations of the outside world. A beam of laser light measures the separation of the mirrors. The beam is split and sent toward mirrors at the end of each arm. If the arms are precisely the same length, the returning beams cancel each other out, and LIGO's detector sees no light. But a passing gravitational wave would stretch one arm and squeeze the other. The resulting discrepancy is tiny, a fraction of the width of a proton, but enough to misalign the beams and light up the detector in a rhythmic pattern. On the 14th of September 2015, LIGO detected a flickering light and turned it into a sound wave. A chirp. It was the echo of the marriage of those two black holes. A cosmic cataclysm that happened 1 billion years ago. Hearing a gravitational wave has opened up a new kind of astronomy. For the first time, we have ears as well as eyes on the heavens. And LIGO is only the beginning. In January of 2016, the LISA Pathfinder spacecraft arrived at its destination, a spot in space 1 million miles from here, where the gravity of Earth and Sun cancel each other out. A quiet place to attempt the impossible, keeping 2 cubes of gold and platinum in perfect freefall and perfectly still. The mission is a test, groundwork for a future mission, ELISA. 3 spacecraft 1 million kilometers apart, linked with lasers, lying in wait for gravitational waves. The largest instrument ever built would be dedicated to Einstein's elusive waves. From nearby black holes to the first rumblings of the Big Bang itself. From ultimate birth to ultimate doom. Ears tuned to the invisible music of the cosmos.
Absolutely.
You think I'll be happy?
So you might have noticed that event actually happened in September of 2015. It actually happened during the commissioning of the Advanced LIGO Observatory. So LIGO had existed, but advanced refers to some improvements they made to the sensitivity. And during the commissioning phase, they basically turned it on and almost immediately this happened. So they extended the commissioning phase a little bit longer, make sure they got enough data to analyze this, and then they spent all the intervening months until the public announcement, February 11th, making sure they were right and really understanding what they had done. And this simulation that you just witnessed, that's not an artist's conception. That is the real scientific numerical simulation that was used to create this model that fits the data, that is the best explanation for the data. So, we could see the universe before, and we could feel its wind. Now we have a new sense. Now we can hear it. So I just want to zero in on those sounds. You heard it in the movie. So it has the moniker GW150914. Hopefully there will be many more to come now. Let's see if I can get this.
So the machines, these two LIGOs are still working and they're still listening for more.
Yeah, so they took a break to do some more work on it, but they're, I think, about to, or maybe have started up again. I'm not sure exactly when they were, flip the switch back on. But the really exciting thing, they only had the two, Washington and Louisiana. The really exciting thing is that they're very soon going to have another one. There's a separate consortium that they collaborate with called Virgo in Europe. And once they have three, the exciting thing about that is that you can figure out where the signal came from. So when you only have two, you basically kind of get a streak of possible originating locations. But when you have a third, that pins it down to a small region on the sky, and that's going to be super exciting because we'll start to be able to figure out where's this thing coming from.
When will the one in Europe be up?
I believe that they are planning to do that within the year. So I don't remember the exact date that was their target, but I'm thinking like fall, something like that. So let me see if I can get this to respond to me. No? Okay, so for some reason I'm just going to have to. This worked earlier when I was showing it to them, but it's being fussy. Where I'm pressing. So this is going to be a little bit of a random trial and error, but what I'm trying to press is the real event. So this is converting the gravitational waves into sound. And unlike radio waves, when those are converted into sound, the wavelengths are completely different. But in this case, the gravitational waves can be played at the frequencies are the same as the human hearing range. So they can be played in human hearing range. However, the audio equipment in most, art museums or auditoriums and so on are not really good enough for the natural frequency they occur at, which is quite low. So it's very hard for our ears to hear and get a really accurate rendition of low frequency sound. So what they've done in these two recordings is shifted them up in pitch to make it just a little easier for our ears. But it is a genuine auditory signal, even in the original. All right, so I'm playing first the real event. That's what you just heard. Well, so let me play the model. So the real event, of course, has lots of static and noise underneath it, and then the event is embedded in that. The model is just purely the thing that you're listening for. So I'm going to play that so you can know what you're listening for, and then go back to the real one. All right, so here's the model. You hear that? It sounds a little silly, just a little chirp, but that is 230 solar mass black holes merging. And I think that he said in the video something like it's the energy of 1,000,000 trillion suns. But remember that the sun is really inefficient at creating energy. So most of the sun will survive after the sun is done turning mass into energy. So Einstein has this equation, we all know it, equals mc squared, right? So the most efficient way to turn mass into energy is to directly convert mass into energy. The sun doesn't really do very much of that. In the sun's reactions, a very minuscule percentage of actual matter is turned into energy. But that event may sound like a lot, 1,000,000 trillion suns, but it's also the equivalent of taking 3 suns and turning them completely into energy, vaporizing them completely into energy. 3 suns worth of mass, which to me that's cooler, but it's the same statement. All right, so one more time, here's the model, what you're listening to. Now listen for it, try to hear it in the real event. Did you hear it? I'll try one more time. So that is the first time that astronomers, that the human race as astronomers has heard the universe. All right, so the first sound actually came from about 1.3 billion light years away. In terms of the cosmic span of history, that's not very far away. 1.3 billion years sounds like a long time ago, and in terms of looking back in time, of course, you know, that's before humans, but nonetheless, that's our cosmic backyard. So the source was actually pretty unexpected, and this is sort of what this has to do with my research, because I have not been a gravitational wave astronomer. I'm not associated with LIGO in any way. But the source was not what they expected at all. No one actually knew that black holes with masses 30 times the sun even existed. They speculated as to whether they might exist, but there was absolutely no observational evidence of black holes with mass 30 times the sun. There's black holes much smaller in mass, and the supermassive black holes at the centers of galaxies. But this kind of middling huge, but nonetheless kind of star mass kind of black hole, nobody even knew they could exist, and they were not expecting all the event rate calculations that they made predicting what LIGO would detect. This was not in that. So not only were they not expecting one, but let alone a pair, right? Now we got a pair of 30 solar mass black holes where we didn't even expect one of them. What does this mean? Well, so this event points to very massive stars, because the remnant of a star, the black hole is the death remnant of a former star that had to have been much more massive. The remnant is always less massive than the original star. So we're talking about 2 hugely massive stars, and they had to have been born together, because stars that are very massive burn up their fuel and die just like that. Their lives are over very quickly. So they had to have born together at recent times, because remember, this is our cosmic backyard, and that's despite the fact that in terms of cosmic history, our understanding as astronomers is that star formation is winding down, that the peak of cosmic star formation was actually in the past. So why is this the first thing we heard? Well, excitingly for me, my recent work, which is using just light waves, I do use the full span of light waves, but I have not used anything else, has found that isolated small dwarf galaxies, so much smaller than our Milky Way, more like if you've ever heard of or seen the Magellanic Clouds that are satellites of the Milky Way, those kinds of small galaxies are called dwarf galaxies. So I found that these small dwarf galaxies, when they're isolated, not the Magellanica clouds that are near our galaxy, but when they're far away from anything else, are basically late bloomers. That these are actually forming most of their stars now, and have actually rapidly doubled their stars in the last billion years, which is exactly the time period that's relevant to this discovery. So I'm super excited about this, and hoping that maybe I'll add gravitational waves to my toolkit in coming years. So what does this have to do with art and the art exhibit? Well, so we have over here, in fact, the actual physical objects, but here's a blown up image. We have two pieces from Dario Robledo that have to do with sound and hearing. So in the first place, we have the first mechanical tracings of heartbeats. So sound converted into tracings that were made by a machine. This machine was called a sphygmograph. And these sounds were lost, but he found these tracings and really wanted to recreate the experience of hearing these heartbeats. And so he collaborated with people to actually figure out how to regenerate the sound. And my understanding is that he came here and played these sounds in a lecture. Maybe some of you went to that? Anybody go to that? Cool. So yeah, so some of you might have heard it, and if not, my understanding is it will be posted on the web, so you can go and hear those sounds. And these, I don't know if you can see these dates. This is 1853 and 1870. So you would be hearing the sounds, the heartbeats of people from 150 or more years ago, which is kind of amazing. So those are lost sound waves, but now twice new. They were new the first time they could be recorded, and now again new, as having been rediscovered. Also, from the same artist, we have fossilized extinct prehistoric whale ear bones. I don't know if this was obvious to you that this is a whale ear bone. It's not immediately obvious to me. I had to be told. However, hopefully future civilizations that discover this time capsule will be much cleverer than I, and immediately apprehend that these are whale ear bones. What's cool about them, I think, is his perspective on them in terms of a sense of hearing that we've lost. So he says, what did they hear? I just love thinking about it. It's a sound we'll never ever know, but this is the thing it needed to make the sound. Of course, this has all the more poignancy when you think about whales as incredibly intelligent creatures that communicate over long distances, and imagine that that sound was not just, a random sound, but communication. So my question that I want to leave you with to discuss is, what does it mean to art or science or life on Earth to gain or lose the ability to hear? Or any of our senses? And what will that mean from the point of view of the time capsule as we think about 100 or 1,000 years from now? What senses will we have gained or lost in that time?
Thank you, Sheila, so much. I'm going to pull a couple of chairs just forward so we can talk with you all and ask questions. And then first, I'd like you guys to all stand up, if you would, and let's actually go look at the physical objects together. Because I think scale and also just seeing the delicacy of this drawing might be helpful. So these are Dario Robledo's pieces. So you can get close to it. I've seen them already. Those are the fossils of the extinct whale ear bones. And these are the tracings of the first recorded heartbeat and also flatline. So if you think about those two images together, it's a kind of signal of life and then the cessation of life, the end of life, right? So it's a kind of a beginning and an end. But it's also, like you said, Sheila, a way of understanding a relationship between looking and hearing, right? So this is a visualization of something that we hear. You can all, if you put your hand here, feel your own pulse, right? So imagine a drawing of that, and that's what we're looking at, except that it's the first time. So like the LIGO mission, this is a first time that we have the instrument, or we have the ability to enhance our perception to actually get that. And the whales probably had it for a really long time for us. So once you've all had a chance to look at that up close, I'd love to just start. I'm going to ask a couple of questions of Dr. Kannappan, and then I'd love for you all to jump in. So take a moment. Observation. This is like a lay person. I am not a scientist or anything. This is completely superficial observation. But in both Dario's heartbeat rendering and what you shared with us about gravitational waves, we're essentially looking at the same kind of drawing, the same kind of undulating thing, right? So what about this sense of time that's being communicated there? Those black holes were, a long time ago, and then we have a human scale of time. So can you help us tease that relativity of time a little bit?
This isn't exactly answering your question, but waves are just the stuff of our existence. So the word, I guess, probably originally comes from water waves, but in addition to electromagnetic waves and sound waves and light waves, we already talked about light waves, gravitational waves, all those that we discussed, there's many other types of waves. I think it's one of the most, in a dynamic universe, that's sort of the default. If things are changing, most often the way we describe their change, for example, the waves in your brain, or, in general, when things are changing, they are described by waves. It's one of the most basic mathematical forms that we use in physics or other sciences. I think all sciences use waves very liberally to understand even things that don't seem like waves. For example, a spike can actually be described as a superposition of waves of different frequencies. This is, in mathematics, we talk about Fourier transforms, which the handful of you who raised your hand as scientists will nod your heads, and the rest of you will think I'm crazy, but you can actually superpose a whole bunch of waves of different frequencies and get something that looks nothing like a wave, but it's a wave. It's just because all those different waves have reinforced it at one point and then canceled out in other places.
So waves are the stuff of life.
Waves are the stuff of nature and change and transmission of information, and they're just ubiquitous.
So are there so you've noticed this similarity of waves in these artifacts for the time capsule, obviously also in your work. How else could these objects relate perhaps to questions of space or time, or how we understand ourselves in the present versus the past and the future?
I guess, so let me say, so how could the objects relate to ourselves in the future? One thing I'd be interested in other people's thoughts about is, it occurred to me that, the particular waves that we think are significant, it may seem really obvious to us now because we do have particular senses now, which waves are important. But in the future, maybe a different set of waves are what's important. And I was really thinking about those heartbeats that even in, if you go down, I hope some of you get a chance to look at the rest of Dario Robletto's exhibit. Even within that exhibit, he has an example of, I guess it was 2013, somebody experimented with a beatless heart.
A valveless heart.
Valveless heart. So it has no heartbeat. It's a valveless heart, and it just continuously circulates blood. And it was an artificial heart that was implanted in a terminal patient. So I think he only lived a short time, 5 weeks after having it implanted. But nonetheless, he was alive, and he had no heartbeat. And and then you mix in all the stuff of sci-fi, but it's real things like cryogenics or cloning, and these are things that people are actually working on, right? And so the whole notion that those waves are even important could completely change by the time they may not define life or death at all. And so they look back at us now and say, well, why were they so obsessed with heartbeat waves? But
Right, so Dario, for those of you who didn't get to come to the talk, gave a whole kind of timeline presentation of the history of the human heartbeat. Obviously, it has a whole poetic significance to us as humans. It helps define our humanness. But he was also kind of charting the social history of the human body and science itself. And much like this LIGO mission, when we change the scientific tools or the instruments that we can use to detect something, then what becomes meaningful also changes. So we find different signals to interpret. So in this work that he had done, it was the significance of the human heart and the heartbeat, the sound and waves that it produced, which then the future of that, the postscript, is that maybe in the future we don't have that organ, which we think defines us so essentially, right? Imagining life without a heartbeat is kind of a little bit hard for us to imagine, but also a possibility, yes.
But now science sees the heart
As the electrical.
they see it electrically. It's
Right.
actually nuclear, but when they analyze it, they see it as a producer of electricity.
Right.
And so that's why you got an electrocardiogram instead of listening to the sound wave. Now we look at the electrical pulses that
Right.
comes out, and that gives a much more detailed study of the workings of the heart.
What's fascinating too, to that point, is that so we've evolved the tools to kind of pick up on more sensitive things, but the early scientists were really looking at it mechanically. However, those sounds couldn't be detected. They were described visually on cylinders, wax cylinders, and also cylinders coated with other substances for almost 200 years, and they've just developed the technology last year to play back those early recordings. So again, a kind of time capsule, something that's a message left to us, and hopefully we have the tools to interpret it. So
yeah, and I mean, not to be pessimistic about the future of humanity or anything, but if we were to have some horrible war and LIGO were to be destroyed, that instrument represents the collective technical expertise of a vast number of many hundreds of really brilliant people over 30 years. So that integrated scientific achievement would not be trivial to reproduce. We could lose our sense of humor, So just also thinking, just like the whales, like not every sound can necessarily be reproduced, and that's something to think about in terms of a time capsule for the future too.
So Dario's piece, it takes some kind of unpacking, but it allows us to interpret something from the past in the present, right? Something that a fossil, we need to know that what a whale is, we need to know that it has hearing, we need to know that they communicate intelligently, et cetera, right? So now I want us to all maybe speculate, like to your point about the fact that our faculties or our senses might change. How could we interpret these particular artifacts from the time capsule 100 years from now or 1,000 years from now? So Debbie's going to pass out pieces of paper. We can talk about this too. This isn't a private exercise. This is an imagination. How would someone 1,000 or 100 years from now make sense of that fossil and that drawing on the last slide?
Would whales still be living?
Right, so let's start asking some questions. Would whales still be living? What else would determine if these objects were meaningful?
I have some pencils if anybody needs a pencil.
Would we have, your question, if I can paraphrase it, would we have a sense of hearing? Right?
Well, so I'd love to, okay, now that I've been pessimistic, I'd like to be super optimistic about humanity's future. I'd like to imagine a future in which we become so aware of other intelligences other than humans that we have actually come to respect and communicate with whales. Could that be a future? And then maybe that would give these a whole different significance as maybe sort of a premonition of the importance in the future of whales hearing. Perhaps people looking back would even think that we already knew that we were going to be able to communicate with whales because we had saved these.
I like the optimistic version a lot better. Do any other questions come to mind?
I'm a little late. How far in the future are we talking about?
100 years and 1,000 years.
I think what happens when any sense goes away, any other sense is intensified. So if you think about losing the ability to hear, the other senses kick in a very different way, and that speaks a lot to thinking about what you were saying with the heartbeat. We're used to seeing on, I don't know the scientific term, the cardiogram or whatever it is, and now not having that noise. If it's just a constant whir, what does that look like? So it changes the emphasis depending on if the ability to hear goes away or intensifies. Everything else becomes lesser or greater. I don't know what that looks like, but.
So imagine that, yes?
What if we evolved where that graph of the heartbeat wasn't even considered, it wasn't a measurement. I'm thinking of, I read about a child that had a fraction of his brain, but he could function completely normally.
Wow. Very interesting question. Yeah. So, okay, so let's try to imagine that we are writing a description of these objects from the vantage point of someone 100, take your pick, or 1,000 years from now. So you have that object. How would you describe it?
We don't know the parameters of what they're going to, how they're going to view things. I mean,
So imagine some parameters. What do
Yeah, I
you
think you
those
should just pick an
parameters
imagined
would be?
universe, whether it be optimistic or pessimistic.
Pick a
Pick a
pessimistic or
version of our
optimistic.
future.
I would like to use the past,
Okay.
and it's only, within 3,000 years that there's been any recorded history.
Right.
Before that, it was all verbal, people
Right.
memorized. The Iliad and the Odyssey was verbally transmitted. It was a poem, essentially. And then eventually they wrote a language came about. But now we have lost that ability to memorize. Before, the only history that was that moved through time was only what people could remember.
You know what? What you're saying so resonates with something that really worries me, which is that so much of what we understand now is saved in electronic form. And in my short lifetime, I've already seen every form of media that information was saved on become obsolete and unreadable. And so it's really scary to think, okay, now we have this fabulous simulation of the merging black holes, but that's stored on some computer, and at some point, is that information going to be lost? And maybe it's not even that far in the future that that's lost.
What if you just turn off the electricity and we don't have any of it stored? I mean, if
Well, no, they can be powered off and it's still stored, but you know what I'm saying? Like things
Yes.
like the form of the architecture and so on can change, and then if somebody really wanted.
Will they find something they will say, well, we were able to take this computer and play something, play the Beatles off of this disc, just like we're playing the heartbeat off of that.
Well, but they had to reinvent the technology essentially in order to replay those heartbeats.
That's right. Well,
so you have to reinvent the older computer technology to get back to that old information.
Exactly.
But we do.
Yeah, like you're saying, I mean, NASA had a lot of information and something or another, and they didn't have the equipment to play it on.
But we do have in these artifacts material, but they're material recordings, you can call them, right? So
Well,
they're
we'll have-
analog still.
There may be, they'll dig up a CD and then have to figure out
It's possible,
and then they'll have to figure out reinvent the technology.
right,
To-
because
to
of
read
obsolescence. Right, one of the artifacts in the time capsule is a Discman, which is kind of funny, but also this pessimistic view, right? That we don't even use Discman anymore. This is from 10, 15 years ago, right?
You considered
But-
that object, didn't you? We were interested in perhaps using that object.
Well, it seemed that there were no headphones, but then I came here and I saw there were headphones. It was a separate item.
It is a separate item, yeah. But so, anyhow, there's no right answer here. The quest is to imagine how someone could, 100 or 1,000 years from now, make sense of these material artifacts. Especially, thinking about this idea of waves that you helped us understand today, gravitational waves. Could that be relevant? So,
And we would love for you to, fill out these messages to the future, because we have our message to the future board here that we're going to post them on. And then for the next talk, we're going to look at them through this different lens of the anthropologist, then the archaeologist. And so we feel like it'll be really interesting the time capsules will really be brought to life by your words. So we're just encouraging you to do that. And then Cora's going to take you around to see some of the objects and the time capsule objects.
yeah,
Sure.
so it can even be a question. It can be like, I wonder if we're going to have a sense of hearing, to recognize these as, anatomical relationships to another life form's sense of hearing, right? So we recognize those as related to an ear because we have ears, right? So,
There are also whale bones sitting in North Carolina.
there are.
I mean, those are just all by themselves. If this place was to be buried in rubble and they were to find those in this context, that's very odd.
They're
Because you don't
totally-
have the rest of the animal with it.
Also, those were discovered not in the ocean. Those were discovered exactly as you're describing, embedded in a geological strata on a mountain millions of years later because the earth moved.
Was the rest of the whale there with it?
No.
No?
I mean, maybe some of the bones, but
But
not
it
really.
was a seed that the whale was laid down in.
Right, and then
it moved.
that moved, right.
But
Exactly.
maybe also they were found somewhere nearby and they were used as adornment. I mean, if the rest of the whale isn't there, and it's just this thing, then maybe somebody was wearing it as a necklace or something. Maybe it was a signification of their status or something.
Well, so in case this helps you at all with your task, which I admit I find your question very difficult and I get more time to think about it than you did. But in case this helps you at all, I will tell you that as astronomers, because we don't get to do experiments, a lot of how we understand the universe is essentially kind of a glorified form of storytelling. So we're forever talking about scenarios and testing scenarios, just trying to put together the pieces so that they tell a story. And in a way, that is what a future person who found all these things would have to do. And their scenario might be totally wrong, but you could still imagine, what they might put together. Because as humans, we are storytellers, right? Whether scientists or no. And I think that's, especially with a time capsule created of art objects, some of which are more abstract and some of which are, maybe not even of the present day and so on. It is going to be a challenge for those future finders to tell a story.
That's a very helpful way of describing what we could be thinking about. Thank you.
1,000 years, though, seems like such a short time. I mean, if you think about people 1,000 years ago, we have a pretty good handle on how they lived. And at the time, 90% of the world population was illiterate. They weren't writing anything down. And, a lot of people still were, but we pretty much know how they lived. And, I would hope that people 1,000 years from now know a lot more about us than we know about people from the year 1000.
Right. But, with the acceleration of scientific knowledge and technology, even in the last 50 years, think about all the breakthroughs that are happening. Right. So if that keeps accelerating, then maybe 1,000 years will be really different. We might be unrecognizable to ourselves.
There is a documentary on, I think it's called Into Eternity, and it's on Finland that decided to store all their nuclear waste. And it's going to last about 100,000 years before it's not dangerous anymore. So the movie was largely about how they were going to warn people 100,000 years in the future not to dig this stuff up. Because, they said probably all of our languages now will be gone, or will change beyond recognition.
It's a really interesting problem is how do you communicate with the future that you don't know what their means of communication are.
A time capsule that you don't want to open up.
That is a time capsule you definitely don't want to open up. Does anyone have questions for Dr. Kannappan? Anything from this talk while you're ruminating on this?
It's unrelated, but I read that the Chinese and several other countries were building apparatus to produce gravitational waves. Would confuse me? It's certainly wonderful science, but would it lend any, could you interpret it or figure out anything about gravity so that you would know how to use gravity, or if there are gravity waves, is there some way that you could harness gravity or understand the mystery of gravity? Because Newton just really nobody's really come up with what gravity is.
Well, so there's two separate questions embedded in there. I mean, one is, can you learn something about gravity? And yes, this was the ultimate test of Einstein's theory of gravity. And, this is something that people have been looking for decades, partly just for that basic understanding reason. Because if we could never find gravitational waves, that would leave us in doubt as to whether that theory was, really right. Now, it could be that it's not the ultimate theory of gravity, and maybe there's an ultimate theory, but that ultimate theory will now have to include
gravitational waves.
And
that may be a key to understanding it.
Right. But then the other part of your question, can we harness it? I don't know that you want to harness something powerful enough to create gravitational waves. Because the things that create gravitational waves are just so incredibly powerful that they are not, at least intuitively to me, not compatible with life. That's not to say that my imagination may not be limited, but
but the understanding of gravity is a mystery, and the waves may lend some sort of key, or you can run some sort of test or something to learn more about gravity, that only on a smaller scale.
Yeah, and one of the cool things about it is that, which I had not fully appreciated until I started hearing, honestly, the kind of pop science discussions, because, like I said, I'm not a gravitational wave expert, and this is now something where I'm like, oh, cool, maybe I need to become one. But it turns out that gravitational waves can propagate much better than any other kind of wave, because if you think about, for example, okay, so I told you neutrinos go through everything. That's true. However, neutrinos, even, and that's not even true for light. Light gets attenuated. Like anybody who's seen the sunset knows, light goes through anything and it starts to get scattered and dimmed and so on. So neutrinos are the best prior to gravitational waves. But even so, if something generates neutrinos, like say a supernova explosion, the neutrinos go out in 3D. And so as they spread in 3D, they're spreading over the surface of a sphere. And that sphere, as you go further and further away, that sphere is getting bigger as the squared power of its radius.
Right.
However, gravitational waves, like as two black holes are circling each other, they are generating gravitational waves that are essentially a two-dimensional phenomenon. I mean, not truly two-dimensional. The video showed it's kind of a flexing of space-time in full 3D, but the propagation is outward in a planar sense. So the drop-off is 1 over the distance, not 1 over the distance squared. So, which kind of makes it all the cooler that the first thing we heard was nearby, because we could have heard it from further. Like, this has the potential. There's really much less of, if I were to walk over there, my voice would sound a lot softer to you because it's going to drop off as 1 over the distance squared. But if I were able to speak in gravitational waves after killing you, if I walked over there, my voice would not be that much weaker, only by a factor of 2, because I'd be twice as far away, and not by a factor of 4, like the way sound normally moves. So that's kind of cool. And the other thing is that nothing we know of has the ability to diminish gravitational waves. There's nothing like, the dust that obscures light, or even neutrinos interact a little bit, but gravitational waves just go. They're space-time rippling. There's nothing to stop space-time from rippling.
So that changes our understanding of galaxy formation that much more?
Well, not yet, but it will.
But it
I
will.
mean, we're going to basically get information that cannot be altered or diminished in any way. And it can go all the way back to the beginning of the universe. There's nothing to prevent us. The very earliest moments of the universe, we can't see, right? There's no electromagnetic radiation that can get out from those very early times, but we could get gravitational waves.
When you're saying the wave actually changed time as well as space.
Well, space-time is integrated.
Right.
So in that sense,
With gravity.
yeah. So it's not. I don't want to give you the sense of it's not going to.
I understand.
At least not in my understanding. It's not going to make us be able to do anything funky with time. It's just that when space stretches, that also alters the exact length of the time interval associated with
Right.
it.
Right.
Yeah.
Does anyone else have any comments or questions or thoughts?
I want to ask a question about the two samples that we heard. Because you had one that was isolated, and then you had the one that had what I'm going to call fuzz.
Yeah. So one was real and one was a mod.
What's the fuzz that we're hearing?
That is because when you have an instrument that's trying to detect something super faint, there's always just the instrumental noise.
Okay, so it's just the impurity in the instrument itself.
That's telling you that that little chirp you heard, because you could barely hear it, that's telling you, that's about the signal strength we need.
That's the sensitivity.
That's the
right
minimum
there.
that we need to be able to detect it, because below that it would be in that noise.
Okay.
In that fuzz. And these future instruments, like they showed the space one, the main reason they want to go to space and have things that absolutely can't be perturbed at all and have these huge distances and so on is to drive down that noise.
So the longer the beam, the longer the laser beam, the more sensitive it'll be to detect the movement.
That's true.
Yeah.
Yes. Yeah,
So
and plus the more it's isolated and not perturbed in any way, nothing else can change the length
No
other than the
fuzz.
gravitational wave.
I was
really
thinking
hard.
the vibrations of the earth. I mean, or the truck driving down the road. It's
Right. Yeah. None of that. You can't have any.
Right.
Yeah. So that's why this has taken 30 years for them to get to this point, and they were just so excited because all they had was predictions, and they said, okay, once we get to advanced LIGO, we should actually finally detect something. And they flipped the switch, and it was immediately. There it is.
That it's like discovering the camera obscura. You're barely seeing anything at this and in 100 years, it's gonna be like a symphony. This will
Oh,
be-
yeah, this is another one of Dario Robleto's pieces that I thought had a nice synergy with this. Did you listen to the one where it's like the first like phonograph basically, right? From Edison? And so he's recording a choral work. And I mean, you can barely hear it through the noise. So it's exactly like this.
And how many years ago was that?
I don't know.
Less than 100, right?
It
Was
was
it?
in the late 1800s.
It was about
Yeah.
2050.
Yeah, I can show you guys that piece if you like.
It was the first one, it was the Crystal Palace one in London where he recorded this choral.
Yeah, and now we have what, triple D
Right.
CDs with the ultimate audiophile noise purity.
The 3 satellites they're going to put up, what is that project called?
So there's 2 satellite projects they mentioned. Let's see, so the one that had the long distances was Lisa. And what is the name of the other one? Oh no, that's Elisa. Sorry. And I think the one where they're holding the 2 gold cubes very still. That might be just a precursor to Lisa.
So how far apart are these things going to be, these satellites? And are they going to be shooting lasers at each other?
Yes, right. It's the same basic design. It's a laser interferometer, except with 3 stations instead of 2, because of course we want to localize to an area that is small enough to then go point normal telescopes at it. Yeah.
Right, so I just want to let you all know, thank you again so much.